Alright, so the last section in Chapter 6 that I'd like to go over with you guys is confidence intervals for population proportions. The first two sections we talked about confidence intervals for the population mean. So this is when we have quantitative data and we want to estimate the mean of that entire population. But sometimes you don't have quantitative data. Sometimes you have qualitative data. So let's say my population is the students at CHS, and I want to know the CHS student car colors of their car. Well, the CHS student car colors, it would be difficult for me to record all of those by myself. That would take quite a bit of time. So what you're going to do is you're going to get a sample of these car colors, okay? And let's say I want to find the proportion of car colors that are blue, let's say. So P is the proportion that is blue. Now P is of the population, so this box represents my population. P is the proportion of the population that is blue, and P hat, I have to write a little small there, P hat is the proportion of the sample that is blue. So what effectively we're doing is we're using P hat to try to estimate what the proportion is, just like we used X bar to estimate what mu is in the first two sections here. And really, the same steps are the same, it's just you're using slightly different notation and formulas to get there. So basically, we're going to estimate a population proportion, P, and the point estimate for a population proportion is P hat, and yes, that is pronounced P hat, which is X over N. And X is the number of successes, and N is always the sample size, right? Lowercase n is always sample size. Okay. So, to know and how to continue this formula here, and to get into what we're going to do, the point estimate for the population proportion of failures, this is for failures, is Q hat. And this is really similar to when we use Q for binomial distribution, if you remember that in Chapter 4, which is 1 minus P hat. So basically, we just take whatever P hat is and we subtract that from 1, because if it's not a success, we're going to consider it a failure. Or if the car is blue or it's not blue. There's no in between. And a C confidence interval for the population proportion P is, we're going to take P hat and we're going to subtract a margin of error. So instead of X bar, notice how this is P hat. And then we're going to take P hat and add a margin of error. And to get that margin of error, because we don't have a standard deviation, standard deviations we can only get from quantitative data, but we have qualitative data. So instead what we're going to do is we have to use z-scores. And this is going to be a z-score all the time. So unlike the population mean, when you estimate the population mean, you kind of had to choose between when to use T or Z. We had that flow chart. Population proportion, if it's talking about estimating a population proportion, it is always a z-score. So it's a z-score for that confidence level, and times the square root of P hat Q hat over N. Okay, and as always, the probability that the confidence interval contains P is C, and that's before, remember, we call it a probability before we create the confidence interval. And why do we use a z-score for this? Well, it turns out normal distributions can be used to estimate proportions if NP hat is greater than or equal to 5 and NQ hat is greater than or equal to 5. So if this condition is met, we can use population proportions to do this, or z-scores to do this. So let's just jump right into an example. It says, in a survey of 1,219 U.S. adults, 354 said their favorite sport to watch is football. Now, if you remember, to create a confidence interval, there's 3 steps. The first is the point estimate. And the point estimate now isn't X bar, because now we're talking about a proportion. Now it's P hat. The second step is margin of error. which now is that formula. And the third step is taking the point estimate, adding and subtracting the margin of error. So the steps are all the same, it's just I'm using different notation and different formulas. But the basic framework is still the same to create confidence intervals. So we want to find a point estimate for the population proportion of U.S. adults who say their favorite sport to watch is football. So p hat is x over n, which is 354 over 1,219. Because there's 354 that like football, there's 1,219 that we surveyed. And this is approximately, and make sure you give enough decimals so that way your final answer is accurate to at least the nearest percentage, we'll say, for this class. So I gave 6 decimals, which is probably a little overkill, but I would say at least 4 or 5. Okay, so that's the first step, is finding the point estimate. And now we're going to construct the confidence interval, a 95% confidence interval for the proportion of adults in the United States who say that their favorite sport to watch is football. So the confidence interval, we already did the first step, so the second step is the margin of error. I'll rewrite the formula again. Okay, now it's a 95% confidence interval, so what z-score goes with 95%? Well, let's do this the long way, and then we'll go with the short way really fast. So if you remember the long way, which you do have to know, is 95% is in the middle. That means there's 2.5% on each side. So if we look at our normal table, it's this one, which is negative 1.9. Negative 1.96. So negative 1.96 is the z-score, or 1.96, remember, because we use the positive, is the z-score for a 95% confidence. Now remember, because this is 95% and that's such a popular one, if you go to the t-distribution reference chart and you look at 95% at the bottom and look at the infinity line, because we have an infinite number of degrees of freedom if we're using a normal distribution. Right here you have 1.96. And that will always happen. So make sure that you see, look to see if the confidence level is at the bottom of the chart first. Excuse me. Okay, so p hat is what we just found, 0.290402. Q hat is 1 minus 0.290402, because remember Q hat is 1 minus P hat. And then we're dividing by n, which is 1,219. And you can put that in your calculator. You may want to do it in a couple steps. So like maybe do the numerator first, divide by 1,219. Take the square root of that and then multiply by 1.96. But when you're done, you should get 0.0255. And the third and final step is to take p hat and add and subtract the margin of error. So that's 0.2904. I'll just round to 4 decimal places at this point. 0.0255, and subtracting 0.0255. And when you do that, you get 0.2649 and 0.3159 after adding and subtracting those numbers. So our sentence should say, with 95% confidence, the population proportion of U.S. adults whose favorite sport to watch is football is between 0.2649 and 0.3159. There we go. And that's how you create a confidence interval for a population proportion. So notice that the same three steps are the same. Point estimate, margin of error, add and subtract the margin of error from the point estimate. It's just there's different formulas, so you just have to know what the problem is talking about. Okay, let's keep going then. So this one, slightly different problem about teenage drivers versus senior drivers and whether which is more dangerous. So it says of 900 U.S. adults surveyed, 63% thought teenagers were more dangerous drivers, 33% thought people over 75 were more dangerous drivers, and 4% had no opinion. Construct a 99% confidence interval for the proportion of adults who think that teenagers are the more dangerous drivers. Well, first step is the point estimate, which is p hat. And the question is, construct a 99% confidence interval for the proportion of U.S. adults who think that teenagers are the more dangerous drivers. So specifically, we're focused on teenagers. And teenagers, according to the survey, it says 63%. So our p hat is simply 0.63. And what I would advise you do is, try to do this as much on your own, and then pause the video at parts if you can, and then come back to it. But try to think about what step is coming next and then play the video. Pause the video, think about what comes next, then play. Okay, so 0.63. Notice I didn't have to divide anything, and some people are like, I thought the formula was x over n. Well, it is, but they didn't give us how many in the survey thought teenagers were U.S. more dangerous drivers. They just gave us the percentage flat out. I could figure out how many people. I could just multiply 63% by 900. I could figure out how many people said that, but I don't need to, because I really just need the proportion, which is 0.63. So they did a little bit of the work for us in this one. All right, margin of error. Margin of error, z-score, square root, p hat, q hat over n. All right, so we're at 99% confidence, and I'm just going to use the shortcut for this one, because at 99% confidence, this one is actually more accurate on the t-distribution chart. So at 99% confidence, infinite number of degrees of freedom, because we are using a z-score, is 2.576. If you use the normal chart for this, you'll get 2.575. 2.576 is actually slightly more accurate. So I'm going to use 2.576. 2.576 times the square root of 0.63, well, minus 0.63, which you could just put 0.37 there if you wanted to, divided by 900. Okay, and when you calculate that, you get, actually I'm going to double check my calculations for this one, because it might be slightly off. 0.0415, and that 5 is rounded up from a 4. Yeah. Okay, so the third step then is to take p hat and add and subtract the margin of error, which is 0.63 plus or minus 0.0415. So when I subtract, I get 0.5886, and when I add, I get 0.6715. So we say, with 99% confidence, the population proportion of U.S. adults who think teenagers are more dangerous drivers is between and I usually round in the sentence, so I'll round that to 59% and round the other one to 67%. Okay. And that's it for finding a confidence interval for the population proportion. All right. The last thing I want to talk about is finding sample size or increasing sample size to increase precision. So you might recall from section 6.1, we took the margin of error formula in section 6.1. So this is section 6.1. We took the margin of error formula and we manipulated it to get this. So we solve for sample size. And what we can do is we can do the same thing here. So we're going to take our margin of error formula. We're going to take our margin, that's just a line. So we're going to take our margin of error formula. And we can solve this for n. And when we solve it for n, we get p hat, q hat, z sub c over e, and this part is squared. Just the fraction is squared. And basically, like this is used for the same reason that we can that we did for 6.1. So sometimes statisticians are approached by scientists and they say, how much data do I need to be accurate within a certain margin of error? Now this formula though has a problem. P hat and q hat are proportions of a sample. So why would how could you answer their question if a scientist comes to you and asks, how much do I need in my sample to estimate this proportion, but you have no idea what that proportion is because you don't have the sample yet, and so to use this formula you need the sample, but the purpose of using this formula is to figure out how many you need in the sample. It's kind of a you're kind of in a circular reasoning here. So what do? Well, this formula assumes you have what we call a preliminary estimate for p hat and q hat. So sometimes you know what p hat and q hat are, or you have a really good idea of what it is based on previous information and previous samples, and you can just use those. But let's say you have no idea. Then what we do is we take p hat, we set it equal to 0.5, and we take q hat, and we set that equal to 0.5. And when we set those equal to 0.5, then that maximizes the product. So it basically puts us in a worst case scenario. It maximizes the product when we multiply p hat and q hat together. It's a q hat. P hat times q hat. And when the two numbers that add to 1 when multiplied together that give us the largest result is 0.5 and 0.5. So for example, if I picked like 0.4 and 0.6, those add to 1, but when I multiply those, that doesn't give me as large of a number as 0.5 times 0.5, which is 0.25. So 0.25 is the largest. So basically, we're giving the scientist a worst case scenario. All right. So let's see what happens when we have a preliminary estimate and when we don't. So we are doing a political campaign and wish to estimate with 95% confidence the proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3% of the true population. Find the sample size needed if 1, no preliminary estimate is available, and 2, a preliminary estimate gives p hat equals 0.31, and compare. Okay, so there's two things we have to do. We have no preliminary estimate in 1 and a preliminary estimate of 0.31 in 2. So for 1, I'm just going to write out the formula again. So p hat, q hat, z sub c over e, quantity squared. So if we don't have a preliminary estimate, as I said, we're going to use 0.5 for both. Now my z-score is 1.96 because that's 95% confidence. And my margin of error. Did you figure out what the margin of error is already? Well, it says your estimate must be within 3%, so that's 0.03. And when you do this, you get 1067.11, but you should remember to always round sample size up, so that's 1068. Let's do the same thing for this one. So again, we're going to plug the numbers in, but now I'm going to use 0.31, which would make q hat 1 minus 0.31, which is 0.69. You could just put that in here if you want. And this is still 1.96 over 0.03 quantity squared. Don't forget to square this fraction, by the way. That's a common mistake. So 913.02, that's so close to 913, but remember, we always round up, so 914 is the answer. Okay, so what happened? Well, if you have a preliminary estimate, you don't need as many people, right? This one had the preliminary estimate, 2 did. If you don't have a preliminary estimate, you need to survey more people, okay? So we can say a preliminary estimate allows for a smaller sample size needed. And that's basically it. Trying to think if there's one thing I do want to mention though, and this is why these things are off all the time. Many times you'll see about political campaigns, you'll see in the polls, it'll say like, for example, way back, Donald Trump versus Hillary Clinton. It's an example probably most recent in most of our minds. And for Donald Trump versus Hillary Clinton, if you remember that election, a lot of people thought Hillary Clinton was going to win. The polls were saying that she's going to win in nearly all places. That's just how it was. Well, that's because their samples were biased, right? If you're called up and you're saying who you're going to vote for, a lot of people won't answer. And that's how they get those calculations. They can't actually get the actual data. So this goes all the way back to chapter 1, where if your data is not randomly collected and is not truly representative of the population, then the math behind it, all of this, doesn't matter. So that's why it's so important to get data that is unbiased as possible. Just like with Donald Trump versus Hillary Clinton, we all know that Hillary Clinton didn't win. It was Donald Trump. And the reason why people were so shocked by it is because the polls were reporting, or part of the reason why, polls were reporting Hillary Clinton was going to win. But that's because their data is always based on these polls based off of biased sampling. Because people that want to give who they're going to vote for are more extreme about it. And that's just how that is. All right. So that is the last section of 6.3 we're going to go over. And that was sampling or confidence intervals for population proportions.